We just started the record. Good evening. So we are at the 12th edition of this meeting. It's a pleasure to see that the meeting has gone on, and hopefully we will run this for one full year and maybe continue this for a longer period. So essentially, today we are completing 1 year as far as this event is concerned. We'll continue to run this for some more time with the participation of everybody. I was telling Suraj that this meeting, we should put all the recordings on YouTube, and so that people, at least from their respective groups, can have access to this, as well as other people across the campus will find it easier to collaborate or to find common threads between groups. This is one of the important lapses in our system, and this is why this was initiated. Let's hope that we can continue. Today we have 4 fantastic speakers and very high quality researchers on campus. We are going to start this meeting first with Ashish Sen, right? This is our schedule, Suraj?
Yes, sir. Dr. Ashish Kumar Sen, first speaker.
Yeah, Ashish this is Swarna Jayanti fellow and is doing fantastic work. We don't have introduction normally, so we will get this started, Ashish, as soon as you can share your screen. We have 20 minutes for the presentation. I will give you a sign after 20 minutes, and you can wind it up in another 5 minutes. So 5 minutes
okay.
Available for questions. We are recording this and this will be available. Yeah, thank you.
Sure. So hope my screen is visible.
Yeah, not yet full screen though. Yeah, okay, good, go ahead.
Okay, so good evening. I'll be presenting acoustic handling of interfaces in microfluidics. I'll be first discussing in the context of dense suspension, and then followed by a co-flow system. So before I get into my presentation, I'd like to briefly introduce acoustic radiation force. So typically one can generate an acoustic standing wave in a microchannel. As you see here, this is the standing wave by appropriately designing the channel and applying the right kind of frequency. So if you do that, and if you have some particles inside the microchannel, they would experience what is called primary acoustic radiation force. And this force should scale as cube of the particle size and will be proportional to energy density, wave number, and a parameter phi, which is a function of density and speed of sound of the particle as well as the medium. Now, in addition to this primary acoustic radiation force, which basically drives particle positive contrast factor towards the nodal plane, which is at the center typically, and the negative contrast factor particles toward the antinodal plane, you also have secondary radiation force, which is coming from the waves scattered from the neighboring particles. And typically the secondary radiation force is a few orders of magnitude smaller than the primary radiation force. Further, you have the viscous dissipation of acoustic energy inside the fluid, which gives rise to acoustic streaming effects. Now, acoustofluidics is a non-contact and biocompatible technique, and that is why it actually holds significant promise in chemistry and biology. So let's first talk about acoustic handling of dense suspension. Blood is an example of dense suspension. And as you all know, blood is a window into health and disease of an individual. In particular, plasma is rich in information. You can see the various kinds of analytes that are present in plasma. And in many detection methods, the interference due to blood cell is of concern. So one would want to separate the blood cells from plasma. And there are various techniques that are available in literature. And among these, the acoustic technique stands out mainly, as I said, it's because of the non-contact and biocompatible nature. So acoustic method for separation of plasma from whole blood has been attempted in literature. But what was missing is the physics of focusing of this dense suspension, which is not very well understood. So if one wants to do that in a microchannel, one would imagine that we can pump the whole blood into the channel and apply standing wave so that the cells would get focused at the center and the plasma would be around it and you can collect it at another outlet. This works fine if you have a dilute suspension. You can nicely focus the particles into a narrow stream and collect the particle-free liquid. But if you have a dense suspension like whole blood, focusing is very difficult. You can see that you're still struggling to focus this particle into a narrow stream. In fact, from our own experiments, we have seen that this focusing is quite limited. And one would see that before even it reaches a maximum cracking fraction limit, it actually reaches a steady state, meaning you are not able to further focus these cells closer to each other. So there must be something which actually prevents this. And when we looked at literature, we found that there is something called Sear-induced diffusion. If you put a suspension into a fluid, which under flow, you would see that the particles in the flow try to go away from each other. And this is because of the Sear-induced diffusion. It shouldn't be confused with the molecular diffusion, which is a very slow process. And this diffusion happens because the particles are in a flow. So we hypothesized that it is the competition between the acoustic radiation force and the Sear-induced diffusion force, which actually govern the focusing of dense suspension. So what we see here is a cross-section of the channel. And so it is the acoustic force which tends to carry these suspensions closer to the nodal plane. And this is being opposed by this Sear-induced diffusion force. And the competition actually yields an equilibrium width, WC, as you see here. So one could actually analyze such a flow situation, starting with the advection diffusion equation. I'm skipping the math part here, but we could discuss if you have any question. So one could arrive at this expression, which actually relates the focusing width of this dense suspension with important parameters, the concentration, the Sear rate, which basically is related to proportional to flow rate, and the energy density. And one would see that with the concentration and Sear rate remaining fixed, if one puts in higher and higher energy, acoustic energy, you could actually focus the stream, the dense suspension more and more. And with a fixed energy density, if you have a higher concentration or Sear rate, it becomes more and more difficult to actually focus dense suspension. And this simple model was in very good agreement with our experimental data. And you can see that for a fixed energy density and concentration, there is a Sear rate. That means there is a flow rate if you want to achieve high throughput, at which you won't be able to focus the dense suspension at all. And you will also see that at a fixed Sear rate, the focusing would be more and more difficult if the energy density is lower or the concentration is higher. We also carried out a full-fledged numerical modeling of this phenomenon, and that is by using the theory of interacting continua, where the blood flow, you model it as two superimposed continua, both for the fluid and the particles. And one could use the continuity and the Navier-Stokes equation to solve for it. And the effect of acoustics on the flow was realized by using slip velocity, which is related to this flux term that is appearing here, which accounts for both Sear-induced diffusion and acoustic flux. The Sear-induced diffusion flux is actually related to the gradient of concentration, volume fraction, and the gradient of the Sear rate and the corresponding diffusion coefficients. Similarly, the diffusive flux due to the acoustic radiation force comes from the acoustic velocity and hindrance function and the volume fraction function. If you want to understand the physics, one can consider the different timescales that are involved. So we talk about the acoustophoretic timescale, which indicates how the particles migrate under the effect of acoustic force, and how the particles respond to Sear-induced diffusion force, which is represented by the Sear-induced diffusion timescale, and how fast the particles are carried downstream because they are in the flow, the advection timescale. So these timescales are represented in terms of these dimensionless number. One is the Strouhal number, which is the ratio of advection to acoustophoretic timescale, and the Peclet number, which is the ratio of Sear-induced diffusion to the advection timescale. And from a design and operation point of view, one is interested in basically two things in a blood plasma separation device. One is how much you are able to focus the dense suspension to, meaning the width of the focused stream, and at what distance from the inlet you actually achieve this equilibrium width. So with a lot of experiment and simulation, we could actually characterize and see that the width of the focus stream is actually related to the Peclet number and Strouhal number, and the length that is required to achieve this focus stream is related to the Strouhal number. So what we understood is that in the limit of very small Sear-induced diffusion timescale as compared to acoustophoretic timescale, you won't be able to focus the dense suspension at all. That means your focused widths will cover the entire width of the channel itself. Whereas if you go to the other extreme, where the Sear-induced diffusion timescale is much greater than the acoustophoretic timescale, you would be able to nicely focus them into a narrow stream, whereby you will be able to extract large amount of plasma from blood. So with this understanding, we are able to fabricate and develop a device. So this is the channel configuration that came out of the study, where here the whole blood is infused and it is focused because the entire device is actuated with sound wave. And after the focusing that happens in the first channel, you extract the concentrated part of this concentrated blood so that the overall volume fraction reduces. And then in the second channel, further focusing happens. And in the third channel, you have really good focusing that takes place. Finally, you collect the plasma, which is cell-free. And this is a video of the actual device. So this is where the acoustics is on, the field is on, and you can see that the blood is focused at the center, where we're able to extract plasma from the side. And this is where the acoustics is off. So the blood actually flows through all the channels. And we were able to actually, with this improved understanding, we were able to work at a much higher flow rate of dense suspension and get almost double the flow rate compared to what was achieved in literature till that point. So that was some work that we did with dense suspension. Next, I would move and talk about some work that we did on acoustic handling of co-flow systems. Co-flow systems are basically, you can consider it as two parallel stream of fluids or liquids flowing in a channel, for example. And such co-flow systems have been used for phase extraction. For example, one could use this to extract analytes of interest or isolate them from some contaminants. They have also been used extensively in microflow cytometry, where the samples are focused for enumeration and detection of these analytes, as well as isolating and sorting cells and other particles. So they are quite relevant in the context of microfluidics. So what we have learned that I was presenting in the opening slide is that if you put some particles in a channel, what you see is the channel cross-section, and expose this to standing wave. If the particles have positive contrast factor, meaning their acoustic impedance, which is density times the speed of sound, is higher than that of the medium, they would migrate to the nodal plane. And if it is lower, they would migrate to the antinode. So the question was, instead of particles, if you have two fluid streams and one is having high impedance, how does it work? So it has been shown that similar to particle, the fluid stream that is having higher acoustic impedance, in fact, relocates to the center. And this happens even when they have a small, very small impedance difference, as small as 1%. So this was known already. And then, so we asked this question, what if, so this was for co-flow systems where the fluids are miscible. So we asked what happens when these fluids are immiscible, meaning they have an interface between them. So we try to understand this from experiments and scaling. What we found was that when you have two immiscible fluid and you expose them to sound wave, yes, the high impedance fluid relocates to the center, but this relocation is conditional. And this relocation happens only above a certain critical energy. And that was what was observed in our initial experiment. And this was verified through different combinations of fluid, silicon oil, mineral oil, with olive oil, silicon oil, dextran and PEG, and so on. And what we found is in all cases, this relocation of high impedance fluid to the center actually happens above a critical energy. So before even studying the relocation phenomenon, we have to make sure that these fluid streams are stable. And we could find that you could establish a stable co-flow in a microchannel when you make sure that the capillary numbers of these fluids are equal. So that is when you see this co-flow, stable co-flow regime. If you do not do that, you would end up generating droplets like that. And this is because of the instability, hydrodynamic instability that is present. And one could characterize the width of these co-flow streams. And it's actually a function of the flow rate ratio and the viscosity ratio of the two streams. So we try to understand that. So one could write down the acoustic force that acts at an interface between two fluids. And this is in terms of the acoustic pressure, compressibility, velocity, and density. And for a one-dimensional case, which is the case here, this actually can be simplified to this form, where the acoustic force goes as the energy density times the impedance contrast between the two fluids times the width and height of the channel. Similarly, the interfacial tension force, one could write the interfacial tension times the height of the channel. One could take the ratio of these two, and which is given here, and we call that as acoustocapillary number. And what we found is that when the acoustocapillary number is greater than 1, that means the acoustic force to the interfacial tension force is greater than 1, then only the high impedance fluid stream would relocate to the center. Otherwise, they would remain as it is, even if you have a small amount of acoustic energy present. So this study actually led to two further studies. The regime where we did not see any relocation, but still we had acoustic force present. We used it for continuous demulsification, which I'll be presenting subsequently. And the relocation regime was actually used for on-demand droplet generation. So in many applications, we encounter where we have this discrete liquid present in another continuous phase. For example, an emulsion. So you can have water in oil emulsion or oil in water emulsion. So one of the objective is to demulsify this such a fluid, and our objective was to demulsify this water in oil emulsion. And for that, we could establish a co-flow between an aqueous stream and oil stream containing these water drops, and we flow them as parallel streams. So one could expose them to standing wave, and if your oil to the channel width ratio is less than 0.5 and your energy density is sufficient and your flow rate is somewhat less, you could actually demulsify droplets like this. So if one wants to understand how what are the forces involved, one could say that these drops are subjected to the acoustic radiation force, which is given by this expression here. One could also evaluate the role of streaming and the non-inertial lift, which becomes relevant because these are deformable objects. So we found that through scaling this streaming and non-inertial lift force, the forces are negligible. So the relevant forces here, initially when the drop is far away from the interface, the acoustic force is computed by the drag force. And when it comes closer, when you have there is a thin film in between the interface and the drop interface, you have the hydrodynamic force coming into picture. And then when the distance becomes of the order of tens of nanometer, the van der Waals force can also be relevant.
You have 5 more minutes.
Yeah. So we try to characterize, understand this process through timescales, acoustophoretic timescale, advection timescale, meaning how fast the drop is approaching the interface, how fast the drop is migrating downstream, and also the thin film drainage timescale when the drop is closer to the interface. So we found that the acoustic timescale and the thin film drainage timescale are actually of the same order from experiment. And that helped us in understanding the requirement in terms of the stream width ratio and the timescale ratio, where one could actually achieve coalescence and thus demulsify such systems. Now, this is what we had seen when you have a stable co-flow and you expose it to sound wave, and if the capillary numbers of these streams are, both these streams are greater than 1, the high impedance stream actually locates to the center as a thread. And when you switch off, then you have this co-flow that reestablishes again. Now, what we had not done initially is that we did not use a small capillary number, but when you use capillary numbers smaller than 1, we saw something interesting. We found that when you actually turn on the acoustics, the stream actually breaks into droplets. So you can generate droplets when you switch on the acoustic field, and when you switch off the field, these co-flow streams is established again, as you can see here in this video. When the field is switched off, this parallel stream actually emerges. So one could characterize the droplet diameters in terms of the properties and the flow rate ratios. One could use this for encapsulation of particles and cells inside droplets. and one could actually direct these droplets into different outlets as compared to the continuous phase. So this is what happens when your capillary numbers are less than 1 with acoustic capillary number greater than 1. So you switch on the field, you get droplet regime, and you switch off, you go back to co-flow. And whereas when the capillary numbers are greater than 1, you have this stream and thread regime, so which is summarized here. So we actually evaluated and tried to understand what the mechanism. So again, the streaming effects were negligible. The effect of gravity and inertia were negligible because of low bond number and Reynolds number. The pressure pulse induced instability was suppressed because the pressure variation were less than 1%. And we also evaluated the role of KH instability, and which we found is that outside the range where it would be relevant. So what we conclude is that it is the acoustic radiation force which actually perturbs the interface and which gets amplified because of the Rayleigh plateau instability. As you can see here, the interface is initially perturbed and which actually grows. And as the growth becomes, these perturbations are of the order of the stream width, the stream actually breaks into drop, and during which this length of this stream actually goes down, producing a jet. And when you take out the field, this stream perturbations actually die down. And then finally, you have the co-flow that reemerges again, and during which the length of the stream becomes stable as the co-flow length. So we try to characterize this in terms of the pinch-off timescale, how fast this neck of the jet is pinched, and the relocation timescale and the advection timescale. And we found that when capillary number is less than 1, the pinch-off timescale actually is less than the relocation timescale, which is less than the advection timescale. So the instability which is generated initially because of the initial perturbation actually grows, leading to stream breakup and droplet formation. And then when the capillary number is greater than 1, we have the pinch-off timescale, which is larger than advection timescale, which is the same order as the relocation timescale. So here the instability is either suppressed by viscosity or convected downstream because of the faster flow, thereby preventing stream breakup. So we also try to verify this from a linear stability analysis. I will not go through this in detail. But we need to close it. We need to close it. Yeah. In a minute. Yeah. So what we found is in accordance with what is presented through a linear stability analysis. The V plus velocity is greater than 0. That means the stream is linearly unstable. And we also found corresponding to capillary number greater than 1, it is in fact convective instability leading to stream thread transition. And where the V minus velocity is less than 0, you have absolute instability leading to stream drop transition. So to conclude, we understood that the interplay between acoustic radiation force and the Sear-induced diffusion force govern the acoustic focusing of dense suspension. The equilibrium width of a focus stream is a function of Peclet number and Strohal number, and the length required to focus suspension is a function of Strohal number. The dense suspension can be efficiently focused in the limit of very small acoustophoretic timescale. And in the context of co-flow, we understood that you can achieve relocation with acoustocapillary number greater than 1, and then giving rise to either stream thread or stream drop depending on the capillary numbers of these two streams. And then one could achieve continuous demulsification in the limit of acoustocapillary number less than 1 by appropriately adjusting the stream widths and the timescales. So I'd like to acknowledge the contribution of my research group and the funding we have received from various agencies. Thank you for your attention. I'd be happy to take your questions. Thank you.
Thank you. We have just about 4 minutes or something for questions. Very nice. Glad that you presented this so beautifully and with a lot of directions forward. One immediate direction that you started from electrophoretics and acousto capillarity effects, acoustic microfluidics, acoustofluidics. These are all directing towards sensors, right? That's one obvious thing. At some point in time, I see that the science that you have just demonstrated can probably distinguish maybe even diseases in let us say blood cells or any such thing, seeing the separation between different types of cells, things of this kind. So all of this is moving towards diagnostics in a big way. So how do you see this field making an impact in technology?
Yeah, in fact, I have not presented here. We have done some work where we are able to isolate circulating tumor cells from PBMCs, peripheral blood mononuclear cells, using acoustofluidics. So in literature, typically, it is, people have used acoustofluidics to separate out CTCs from PBMCs, considering that CTCs are larger in size. But if you look at the size map, there is considerable overlap between, because it depends on the type of CTC that you talk about. Yeah. There's considerably, overlapping size between PBMCs and CTCs. So what we had considered was the mechanical property of CTCs, how they're different as compared to PBMCs. Yeah. So we consider the acoustic impedance difference between the CTCs and PBMCs, and we're able to isolate CTCs from PBMCs. So that is one application where we have made some contribution apart from.
Sure. So you also talked about separation between particles. One with impedance and all. So one of the major important kind of particles. One is this metallic particles. Another is, let us say, molecular kind of particles. One regime is the plasmonic particles. Another regime is the semiconducting kind of particles. These are all the kind of things that we work on. Now, I personally feel that you are getting into a chromatographic regime wherein you can naturally separate metallic and semiconducting particles of the same material.
So the way these particles that I have talked about are actually blood cells. So,
I understand. So what I wanted to say was that this is one direction which, from our side is something that is of great interest. I leave it there, and because time is short. Pallab has a question here. Go ahead, Pallab.
Hello, sir. This is very nice presentation. I have a very small query regarding one of the data where you showed that the stream instability leading to the droplet generation. Can you go to the video? I see that all the droplets which are getting generated are all uniform in size. Yeah, I guess it is due to the frequency which is applied. Yeah. So is there did you see that this instability leading to different sizes, or is there any heterogeneity in the droplet sizes?
Yeah, so that is the beauty of microfluidics. If you just even use hydrodynamics, forget about acoustics, you would actually generate droplets which are highly monodisperse, and this is very challenging, or I would say difficult to achieve in conventional methods. Okay.
Ashish, we'll leave it there, and Pallab, please discuss this matter. And very nice. Ashish, very nice, beautiful, and all the very best to you for continued success. But let's go to the next presentation, and the next presentation is by Aravind Kumar Chandran. he's there. So you will get about 20 minutes. And so go ahead and make your presentation. I'm not going to introduce yourself, that people should be knowing by this time in IIT Madras. Okay, good.
Yeah, great. Thanks so much, Professor.
By the way, he is a roaring, researcher at IIT Madras. That's all that I would like to say. Thank you.
Thanks, Professor. So thanks for this opportunity to talk. And I would also like to thank Suraj and Ashish. Your presentation was fantastic. So now I hope my screen is visible, I guess, right?
Not yet, not yet.
Okay, let me just share the screen one more time.
Pallab, you pull down your hand. Huh? Go ahead.
So is that visible?
Yeah, it is fine. Yeah, go ahead.
Yeah.
I'll give you
Okay,
10 minutes. Yeah, thank you.
Fantastic. Yeah, great. Thanks, Professor. So for those who doesn't know me, I'm Aravind. I'm a faculty in chemical engineering since October 2016. So I'm here for a bit more than 5 years. So I predominantly work on solar energy conversion and storage. I've given some topic for my presentation, but I'm kind of going to talk something slightly different today. Apologize, and I hope you will enjoy it. So what we work on in our group is predominantly related to photo electrochemistry or electrochemistry. Those are key areas of research that we typically focus on, and that's my base and that's my strength. And we use this base to work on many applications. And our key presence is on solar water splitting to generate hydrogen. This includes direct solar water splitting using photo electrochemical system or integrating solar panel and electrolyzers. And this comes under the category of solar fuels. And my group also work on carbon dioxide conversion to fuels. And initially we started with methane and methanol. Now we predominantly focus on syngas and formic acid because of their industrial importance. And I work with Professor Raghuram in chemical engineering on this specific topic. And now let's move on to the top right of this like diagonally. So where you will see that metal air batteries for electric vehicles. These are one of those oldest batteries. Now we have like more advanced battery packs in our labs anyway. So metal air batteries are kind of, conceptually they share the same thing as water splitting. It's exactly just opposite reactions that happen. And with the metal air batteries, we don't have any fundamental research interest. Rather, we are more on the applied and scale up work. And we do work with a few automobile OEMs in the country. And along the battery side, we do work on lithium-ion battery operational safety. Like, for example, batteries recently exploded in many EVs. And we try to kind of work out and try to standardize the procedures for testing so that the battery management systems in the batteries can be made much better. And then we can potentially avoid those thermal runaway and eventually explosions. So we have a kind of significant presence in this area. Like, but this the top right is completely industry-oriented research, and the top left, my expertise is on solar cells, photoelectrochemical solar cells, and also a bit on perovskites. So I do work a bit on perovskite solar cells. However, we are phasing this out completely for many reasons. And light emitters is something which was not in our fundamental research portfolio. Serendipitously, we ended up on this light emitters, which is what I'm going to talk about today. Okay. And here's my group. I also have a kind of a slightly bigger group, and I should thank all of them because they are the ones who did all the work that I'm going to show today. And I'm just an ambassador for the research. And I should thank, prior to even started, everything was possible because of the funding agencies across the country, both government as well as industrial agencies. Now, let me start with the work. So the solar water splitting, I'll just give a gist of a few of our keywords, and I'm going to go into the details after that. So for example, solar water splitting is one of the key areas that almost everyone in the world who work on catalysis is aware of this technology. And at least you will see 5 to 10 people in every institute working on solar water splitting. Either that photochemical or photoelectrochemical. But then the fundamental problem with all of them is we use titanium dioxide or iron oxide or bismuth vanadate. Most of them are oxide materials, and they're very stable, and that's the reason we use them. But then their optoelectronic properties aren't that great. Whereas on the other side, we have the fantastic silicon, which you see on the rooftop, which is very good for solar conversion to electricity. But then the moment we put it in the electrolyte to do water splitting, they decompose. They need all protection layers. When this whole thing wasn't the like research domain, we serendipitously found out that like it was serendipitous discovery though. We were working on vacancy ordered perovskites for solar water splitting, and with some protection layers though. But we found that this specific class of vacancy ordered perovskites, A2BX6 and specifically CS2PT-I6, and we also have like a lot more combinations now. We have gone way far from this compound. This metal turned out to be very stable in pH1, pH14 for several years actually now. Now we have data for 2.5 years. This metal is like damn stable. And this material absorbs the entire sun spectrum. And we use this material to do solar water oxidation process, one half of the reaction. And we have published the work in Gvante, and also follow-up work on a tandem junction came out in Applied Materials and Interfaces. By the way, I'll not be talking about it. This is just a kind of bit of advertisement on what we work on. Then this is another thing. We were working on tuning the electronic or chemical structure of halide double perovskite materials for solar water splitting. And one of my students, like postdoc, sorry, he just like was viewing the sample under UV light, and he found one of the metals to be damn bright light emitting, actually bright white light emitting. And at this time we felt, let's give a pass. Let's not go and explore this material only for water splitting. Let's try to see why it's emitting white light first of all. And then eventually we tried to like dig deeper, and then we did a lot of fundamental investigations. And this is specifically what I'm going to talk today. So essentially this is about a difference between a material which is symmetric and asymmetric. For example, almost many crystal structures, if it is centrosymmetric space group, like typically we expect them to have a charge separation based on like when you shine light, it generates electron hole pair. We expect them to do the charge separation purely based on concentration gradient or electric field gradient. Whereas when you have an asymmetry, there is an additional parameter that comes into the play, which is polarization. And the polarization was the target we had when we started working on water splitting, because when you have polarized material, charge separation become efficient. But then this polarization also led to bright white light emission. So this came out as a research article in Communications Materials from Nature. And this work also fetched SERP Technology Translation Award last year. And let me start with the basics. This is where I'm going to go into the basics. So as a typical double perovskite metal has a formula of A2, M, and X6. There are two M sites. One is +1 and the second one is trivalent. And the crystal structure looks something like this. It's a three-dimensional structure where you can see that there are two distinct octahedra, one formed by the first metal here, and then the corners of octahedra is occupied by the halogen. Similarly, the next octahedra is formed by the trivalent metal site. And they run alternatively. We have monovalent cation-based octahedra, then trivalent cation-based octahedra. And the pores formed by this like network of octahedra in 3 dimensions is occupied by the A site. This is the actual crystal structure. And if you look at the distance between like the metal site and to the halogen within an octahedra, they're perfectly symmetric. They're all the same. The bond lengths are same. They're perfectly symmetric. Now, our strategy to introduce a distortion in the material is the following. Now, the octahedra chain is similar to what I have shown in the previous slide. But now what I'm doing is I've just taken one chain of it, that halogen, metal, halogen, metal, halogen, metal, and I've drawn that here. Now, in the M2 site, for example, the trivalent site, for example, if instead of there are two pink color systems here, I replaced one that by a kind of brown color system. Assume if the bond length between this brown color trivalent atom cation and then the halogen is much larger, then I tend to experience a distortion in the monovalent octahedra. And similarly, you can also do the same thing for M1 site, which is a trivalent site. So essentially, you try to create a mix of trivalent site or a mix of monovalent site. You tend to create a distortion in the other octahedra. You mix the trivalent cations, then you create a distortion in the monovalent octahedra, and you try to mix a monovalent system. You end up getting distortion in the trivalent cation. Now, I'm going to start with a very basic structure of halide double perovskite, which is CS2AgInCl6. And here I'm only depicting the single crystal structure of this octahedra formed by Ag and indium. And you can see that, let me take this indium, and indium with halogen has 2.514 angstrom, and it's the same with all the six octahedra, 6 corners or 6 halogen. And when you look at silver, again, this is like 2.727, and the bond length is same with all the other locations. And the other indium-based one is a replica of this first one. Now let me look at the bismuth-based one independently. Now I've not mixed anything. There is only one monovalent site, which is Ag+, and bismuth is a trivalent site, which is that M2 site, which I've shown in the previous slide. You could see that even with bismuth, you see that all the atoms around the bismuth are all perfectly do they have the same bond length? Whereas similarly the Ag, all the bonds of Ag and Cl, they are all the same actually. Now you can see one difference here. Bismuth and halogen or chloride has a bond length of 2.68, whereas the indium and chloride is 2.51. Now I'm already seeing a difference. Now when I try to mix both of them and I have both bismuth and indium in a single material, then this is how the crystal structure looks like. So the bismuth is symmetric. The octahedra formed by bismuth is symmetric with the bond length of 2.705. So do the indium, it's perfectly symmetric with a bond length of 2.496. But then you can see that there is like all these corner halogens have to be shared. If I have a 50-50 percentage, 3 of them will be shared with bismuth. That's why I represented by light green, whereas the other 3 are represented by dark green. And this has a bond length which is larger. So essentially, I've distorted the silver octahedra, silver Cl6 octahedra, by creating a mix of indium and bismuth. In fact, we have done with indium antimony, bismuth antimony, and we have also changed halogens from chloride. And we've also, in fact, have a mix of chlorides and bromides. And we almost finished all the combinations here. I'm going to talk only about this specific series of material today, which is a representative of all the other work. On the top left, you will see that this is the typical PL emission spectra under a given condition. The pure bismuth Bi, which you can see here has an emission somewhere very low. It's in the like a small one. And then the indium, you could see that right here, the black one, which is also just above this like a small emission right here. However, when I try to have a mix of bismuth and indium, initially there is a small increase, and all of a sudden there is a sudden increase when the indium and bismuth proportion is somewhere between here, these 3 compounds here. Bismuth is 0.2, indium is 0.8, and when bismuth is between 0.1 and 0.2, the emission is like phenomenally higher. In fact, we also did the quantum yield, and there was nearly like almost 150 times increase between the N members compared to the N members. And here we're just showing the images in the normal white light. And in the bottom, they are under the blue light. You'll see that the N members, which is bismuth-based ones, and the other N member, which is indium-based ones, they look dark. And as I keep adding indium to the system, you see that they're getting brighter and brighter and brighter. And at some point, you'll see that they're damn bright, actually. They're damn bright. And here I've also plotted the integrated intensity from the PL spectra. So these things are around like 0.6. So you could see that the N number, when the X is 0, means metal is purely bismuth-based trivalent system. And the X is 1, it's purely indium-based trivalent system. You could see that the intensity is fairly low in the order of 10 to the power 6. The moment when the X reaches somewhere between 0.8 and 0.9, there is a sudden jump. There is a sudden jump actually, and the sudden jump is like, as I've said, nearly 2 orders of magnitude higher than the N members. Now there are 2 things that we need to understand here. One is why there is a broad emission, and why there is a like only at certain proportion of indium and bismuth, there is a sudden increase in the emission. These 2 things, I'll come to it in a bit. But then there is like possibility, people, when we say that when there is a broad emission, many of the reasons, one of the big reasons would be there are a lot of defects. So apparently what we have done was to see if the broad emission comes out from the defects. We have grown single crystals, although the image is not clear here. We have grown single crystals of a few millimeters, and then we try to do the emission spectra. And the emission spectra of the single crystal is also fairly broad. And this confirms that essentially the material single crystal doesn't mean that we will not have defects. Maybe they might be having defects, but then those single crystals, what we obtained, will not be having as much defect as the powders. So the intensity supposedly should be very low. But then even in single crystals, we found that they're emitting like damn bright white light compared to the like their powder compounds. So this essentially kind of like remove the component, like the emission due to defects. It might be something else. And in order to rule out that the defect might not be responsible, we have also did the intensity dependent photoluminescence spectra, and you could see in the left figure. So we have varied the intensity in lux. The value you could see are in lux, and then as the intensity of the light goes up, the PL keeps going up, and that's also the integrated intensity is also shown in the right plot, where I keep increasing the light flux, and then the integrated intensity is almost linear. And this kind of confirms that again, that defects might not be responsive. This is done in powders, by the way. This is not done in single crystals. This experiment is done on the powder samples, and this again rules out that defects might not be contributing. Imagine if you have a defect, this will go away from the linearity. This will not be perfectly linear. It will go away from the linear. It will be downward exponent or upward exponent, depending on the type of material and type of defects. Right. So we kind of ruled out one thing for sure, that is defect. Now, before going into understanding what contributed to the white light emission or intense white light emission, I'd like to also show one more thing, the photoluminescence lifetime. So the photoluminescence lifetime of the two N members based on bismuth or indium, the lifetime was around some few hundreds of picoseconds. And at the value of X between 0.1 and 0.2, the lifetime went in some microseconds. And in fact, it was going all the way beyond microseconds. Our mission's limit is 13.2 microseconds, and we couldn't go further. So that's why we had to stop at that point. This was going all the way, and we extrapolated and we fitted it. They were coming at around sub-milliseconds. They are not phosphorescing, by the way. Let me say it very clearly. It's not phosphorescing, and it is still fluorescing. So you can also see that that's a phenomenal increase. I'm talking about not like a few nanoseconds to a few hundreds of nanoseconds. I'm talking about a few hundreds of picoseconds to a few hundreds of microseconds. So essentially like a 6 orders of magnitude increase in the lifetime. In fact, this is what we all like in the photocatalysis or photoelectrocatalysis community, how I can increase the excited state lifetime so that I can get less recombination and hopefully better photocatalytic activity. And this came out to be true in these kind of systems. Now I've given a prefix, like still something that's not answered is why there is an intense white light emission. And now I've added one more trouble to it. Why there is a significant increase in the lifetime when I have a mix of bismuth and indium. And everything boils down to these things here. One is I have created asymmetry in the system, which is based on the single crystals. And there are few options. In fact, at the beginning, we proposed so many options. Now I'm just proposing only these three because we have clearly boiled down to the reasons. One is the nature of band gap and the parity of the transition in the band edges, and finally the polarization. And we're going to talk each of these parameters and then see how these contributed to the anomalies or the new results that I've shown in the previous slides. So this is done in collaboration with Ranjit from physics. So he did all this like DFT simulations. So one thing is that when you go for the pure, I represent CaIC as pure indium-based material, CaBC as bismuth-based ones, and the mix is shown right here. So the valence band is formed by the silver Eg orbitals, and then the conduction band is formed predominantly by the indium-based ones, and to some extent silver s orbitals too. When you look at the transition, it's not a direct band gap, by the way. Indium is an indirect band gap, but then there is a flat, nearly flat valence band, and it looks like it's a direct band gap semiconductor. The thing is that you see the parity of the transition. This is going from positive to the positive. Now, whereas when you look at the bismuth, you could see that this is the lowest possible transition, and this happens from positive to the negative. So this is allowed, and this is selection. According to selection rules, it's not allowed. And now when I have a mix of bismuth and indium, you see that the band is essentially flat across the conduction band, and so do the valence band. It's essentially flat. And when you have a flat valence and the conduction band, and this is always attributed to the self-trapped excitonic states. And also you can see that the parity of transition is like plus and minus. So plus and minus. And this helps, like on one side, we have kind of obtained the direct band gap nature from the bismuth, and then the other side we also have the like the transition probability, which goes from minus to plus, and which is inherited from the bismuth. Sorry, the direct band gap transition goes from like either CaIC or CaBC, but then the transition is inherited from the bismuth completely. So now this material, which is comprising of bismuth and indium, both has both the properties. One is direct band gap nature. The second is the parity of the transition has gone from forbidden to allowed. And this is a nice thing. Now, let me go on to experimentally show that is this really the direct band gap, because simulation always deceives us in some cases. So here is an indium-based material where you see that the onset of this is an excitation spectra, by the way, and I've given some explanation, which I'm not going to talk about. When the onset of the absorption and the excitation spectra overlap very closely, it is considered as a direct band gap. When the onset is different, then we can like for sure assume it's an indirect band gap. So we can see that the pure indium-based material, there is an onset, although it's squeezed, so you couldn't see it. Both of them like are at the same place. In fact, like the onset of absorption is given in the dotted line, and then the onset of the excitation is given in the red line here, solid line. So both are close by. Now, when I have a mix of bismuth and indium, where indium is still prominent, you see that both of them are overlapping perfectly. As I keep increasing the concentration of bismuth, what happens is that the separation becomes prominent, and that indicates that the more the bismuth I have, I fall in the indirect band gap region. The more I go to the indium, I fall in the direct band gap region. And when you have a mix of them, I fall at some region, like between, let's say, 40% to 50% of bismuth to 10% of bismuth. I have a direct band gap semiconductor. At the same time, I inherit the allowed transition from the bismuth. So these two things come together and assist in bringing out a very high molar extinction coefficient. And molar extinction coefficient is true for both ways, absorption as well as emission. And that is one of the primary reasons why we had an intense white light emission in our materials. And there are a lot of experiments, supplementary experiments we have done, and everything is in
just about 4.5 minutes left. Yeah, thank you.
Sure, sir. And this is about, so now I've kind of talked about asymmetry, nature of band gap, and then the parity of the transition. Now I'll move on to one more thing. What is the origin of these things? What is the origin of this system? Is it, one is our material is distorted. So that is the only thing we know about the structure. So if you want to correlate between the crystal structure to the emission properties, we need some tool. So what you've done is we have intentionally taken the like end members, which are symmetric, which are based on indium and bismuth, and we intentionally distorted them using applied electric field, and we did photoluminescence. So that was a fantastic experiment we have did. We retrofitted our mission and then photoluminescence mission, where we can also apply the bias during the measurement. And we found out when I apply the bias, it's fairly complex actually, but then I will just show one thing. When I apply the bias, you see that with the indium, the emission intensity is going up. And then we've also structurally proved when I apply bias, even the symmetric material becomes asymmetric. Because the bias will tend to attract positive charges on one side, negative charges on the other side. Now, after I stop the bias, the emission tend to go back to its original position. And the same thing was observed for bismuth. You could see that bismuth is going this way. When I apply the electric bias, the material gets distorted and the photoluminescence keeps increasing. The moment I turn off the bias, it tends to go back to its original state. However, when I take the material which is already distorted, what happens is that the photoluminescence changes very little. The photoluminescence changes very little, in fact, a negligible change, because the distortion induced by the electric bias seemed to be fairly less compared to the distortion that we induced on the symmetric compounds. Okay, this again confirms that the most important thing is you have to create a distortion in order to introduce the change in the parity of transition or change the nature of the band gap in order to emit white light. That is the greatest thing about the distortion that we have introduced. And the other thing that I would like to quickly point out is that distortion also created a local polarization. Actually, this was the whole motivation behind why we worked on this whole topic. So we did a lot of polarization measurements. We also have extensive polarization characterization tools. And we found that in the material where the bismuth is 0.1 and indium is 0.9, the polarization varies between 1.4% and 4%. There is an inbuilt polarization. This is not an asymmetric, non-centrosymmetric material. This is a centrosymmetric material, but then because of the local distortion in the AgCl octahedra, there is a dipole polarization. And the dipole polarization turned out to be the most important parameter to increase the excited state lifetime. For example, when I shine light in a symmetric material, it's a normal conduction band valence band separation. However, when I have a polarized sample, let's say wherever the negative charge is accumulated, holes tend to accumulate in that negative charge side. Whereas wherever the positive charge is accumulated in the polarized domain, the electrons tend to get accumulated. And that led to a separation of charges quite efficiently. And then the recombination also becomes phenomenally lower. And that led to a very high excited state lifetime. But then it also gives a downside. Now the electrons are confined to the positive side of the polarized domain. The holes are confined to the negative side of polarized domain. They will have an hindrance to the charge transport, which we are still investigating. And polarization on one side, it's good for charge separation and reduce the recombination. But on the transport side, we are a bit skeptical about it, and we will see how it's going to turn out in few years down the line. We'll be able to answer that question properly. And just to summarize the whole thing, I would like to say that we have introduced asymmetry in the crystals, and this asymmetry in the crystal, essentially distortion, led to the change in the nature of band gap and the parity of the transition, and eventually that also affected the polarization. These three changes in the fundamental properties of the metal led to a significant enhancement in the emission and also significant increase in the lifetime. Now, I also want to show one more thing. We have also tested this concept of distortion universal, and it turned out to be universal. This is the best thing that can happen to it. We found a concept in one material and we extrapolated to the other set of materials. If we found that concept to be true, that will give the best like a satisfaction when we do the science. And almost all the chemists also feel the same, I believe. So we have moved from chloride to bromide, and here I'm showing only one result, where we also mix this indium and bismuth, where we found out that when we have the N members do not show significant emission. However, when you have a mix of bismuth and indium, the emission drastically increased.
We have consumed the time, okay? Yeah.
30 seconds, Professor.
Yeah.
And similarly, we also, as I've said before, when we go to the +1 side, when you have a mix of silver and sodium, we also observe the same thing. And we also observe the same thing in triple perovskites, not just in double perovskites. We have gone from double perovskites to triple perovskites. And we see that when I have a mix of these metal sides, the metal creates distortion, and this increases the emission phenomenally. I want to just conclude saying that distortion is really an important thing. And I think it helps both the white light emission community and also the photocatalysis community or catalysis community in general, where you want to increase the excited state lifetimes phenomenally for your photocatalytic or photoelectrocatalytic reactions. With that, I'd like to say thanks, and I'd be happy to take up the questions.
Well, beautiful talk, very, very nicely done, and one single theme and lots of pointers and different directions. Let me, well, Sundar has already raised his hand, but let me ask one or two questions and then get this going.
Yes, Professor.
These are systems wherein there is mixed valence possible, right? This is indium and this is bismuth containing systems. So there can be mixed valency, and that mixed valency could be something that is interplaying, probably in the last thing, that's potential that you talked about, the distortion. So did you look at, apart from all of these optical properties, did you look at what happens to valence fluctuation?
Yes, Professor. So we have done also, the XPS was the only tool we have used. And there was no significant change when we have this mix. So indium still remained predominantly at 3+, except like we have not observed any mixed valency in any of these elements as such. However, with antimony, we did observe antimony, like it has 3+ and 5+ states. And in fact, when we try to synthesize antimony, in some cases, it knocked this Ag out completely. It goes to CS2, antimony 3+, vacancy, antimony 5+, and Cl6.
Great. So the last question in that context is that when you apply potential or any kind of distortion that you see, the changes are all phenomenal. But that would also imply corresponding change in photochemistry, changes in what one can do with these materials. You know, on the one side, it is the light that is there. For example, you can completely switch off one kind of chemistry, photochemistry, I mean. Or switch on one kind of chemistry. Or this may be something very interesting in terms of conductivity. It may be related to sensing. I do not know what are the different directions possible. What are you looking at? I mean, I know that white light itself is very interesting, but there can be many others too.
Yes, Professor. So I think you rightly pointed out, the only thing that we're targeting at the moment is how to have a good balance of excited state lifetime due to this distortion and good transport. And but like specifically targeting selective conversion or switching of one type of chemistry. For example, in CO2 reduction, we are working on that now. The conversion of CO2 to formic acid is prominent when we have the N members. However, when you have a mix of these two, it's not going to formic acid production anymore. It's going to something else.
Sure,
and
sure.
Which is
Obviously. I know. But the time it goes on. Yeah, Sundar Gopal. Yeah.
A very nice talk. I have two very quick clarification. One is, so do you have any control of the same slide, what Pradeep was asking question on the same slide? So do you have any control that, what about like if you have indium, silver, bismuth, what about indium, and how you have any control? That is one. And the second thing is that you have,
what do you mean by control? Like, sorry, I don't know which slide you're talking about. Is it this one you're talking about?
No. The same slide what Pradeep was asking you question. That this one, yeah.
So if you take simply what Sundar Gopal is saying, just indium alone, right?
Yeah. So do you like alternatively you're getting indium, silver, bismuth? And bismuth and indium being a heavier element, they can also offer a higher oxidation number, a higher coordination number. So those things you do never end up saying all the C is octahedral.
Yeah, so that is the last thing that I've talked about, sir. So that's it comes under the category of vacancy ordered halide perovskites. So you asked like fantastic things, sir. So essentially, it goes into when I try to put like two bismuth in one place, it automatically creates a third vacancy. Or say let me take one of the N members x equal to 0, either bismuth or antimony. I end up with this configuration. I couldn't connect all the octahedra in 3 dimensions. Rather, I have a vacancy of one of the octahedra because one of the bismuth or antimony is absent. When I try to push Ag out and only use either bismuth or either antimony or either indium.
Well, this also points to another interesting point that your structure, you are probing equilibrium structure. The moment you are exciting, there may be dynamical changes in this. And those dynamics are the ones which are essentially giving you the photophysics, associated photophysics, which we are not in a position to see. So I'm saying that there is very interesting structure, that structural changes that are happening with time, especially in the time scales that you are probing. That will be beautiful to really probe.
Definitely.
Some amount of computations are required in that.
Yes, Pras, it would be very interesting to really know the structural changes under the illumination. I think that would be really cool to study all those things. Hopefully, we'll be able to do it sometime.
Fantastic. What a great talk. Very nice. And so thank you very much. So let's move on to the next speaker. We have Karthik Chandra Mandal going to speak to us. He is a fantastic researcher and let us hear him. Yeah. Sundar, you'll have to pull your hand down. Yeah. Karthik, are you there?
Yes, I'm there. Thank you, Officer.
Yeah, the same thing, 20 minutes, huh?
Yeah. Good afternoon to all of you. Thank you, Professor Pradeep, for asking for giving a presentation. Really, is in a busy schedule. I try to make as much as possible. I'm really thankful to you for your supportive words many times. So let me talk about some recent or the last 1 year we're doing some kind of theoretical and electrochemical study on nitrogen binding and the reduction. So this work is theoretical is mostly done by us, and some electrochemical reduction is by Professor Kodanaman's group, and some papers we have taken the system from some professor like Pollard and Bitrand or Peter Jonas and their work. And then we have done theoretical calculations and published some papers, and I'll just discuss about them. And we will also speak about one of our work where we have used nickel catalyst in monomeric form, which can bind to the nitrogen, and electrochemically it can produce ammonia. So we'll where you use experiment plus theory to explore all the portion of the work, and also a lot of mass spectrometry to dig down the mechanistic investigation. Okay. So these are the major areas we work mostly, and Like optical materials, even also we have some white light emitter, like organic molecule based, metal based, some frozen material, single molecule magnet or single ion magnet, and also some of the materials like compounds. They are all molecular, which can bind with the aerial oxygen or carbon dioxide or nitrogen, those kind of things. And I might talk today is mostly on the nitrogen binding today. So what I like to tell you that in the Earth atmosphere and the billions of years ago, 2.5 years ago, it was mostly made of sulfur, and microorganisms developed around the sulfur. And slowly, cyanobacteria, they evolved slowly, and then that time they have started producing oxygen from their biological system, and then slowly over the another some billion years, the air became more rich of oxygen and oxygen atmosphere, and then the iron ore and all of whatever around the surface, it got oxidized and deposited, and also in the solubilized in some amount of water, and then iron system developed. So there is a bacteria which is called what there in our soil. They are free bacteria which take sunlight and binds directly with the nitrogen. They're called some kind of how do you call it, cyanobacteria. And also there is a bacteria called ribosome, and then this ribosome, azotobacteria, the one who actually takes from the sunlight and lives in the freely in soil and can convert nitrogen to ammonia. Okay, they're using the sunlight, and also the another called ribosome, which actually are infecting some of the legume type plant roots, and they live there, make colony, and they are like a symbiotic way. They help the plant to get the nitrogen product, the amino acids, and they also get the nutrients from the plant, and that's where they live. Okay, and all the beans and dal kind of things what we eat, they are actually helped by this ribosome bacteria. And this nitrogen is actually very inert, and we have 78% in here, and only can be fractionally, some of the microorganism can only fix it to ammonia, ammonia or nitrate or amino acid. But the most of the plants,
can you please use your pointer, Karthik?
They cannot really do that. And so what they have actually in common of them, that they have this nitrogenous the enzyme, and where this they have a metal core which have 7 iron and 9 sulfur and a carbon atom in the center and 1 molybdenum. And this molybdenum actually molybdenum 3+, and it has also, it violates Hund's rule, and it is actually is a spin pairing happens because of the iron molybdenum interaction through the sulfur bridges, and this is like peculiar system. So for the last 22 decades, Professor Jonas Peters, their group, they have came up with such kind of model system where they like to study. They start binding the nitrogen, they isolate the molecule, they prove the how it is happening, those kind of things, and electronic studies. And what was missing in this one, no one could say. I mean, they didn't study the type of metal nitrogen interaction or the role of this light element here. And this is the boron is they give the best nitrogen reduction, then carbon, then silicon. Then we tried to do EDNSP calculation. We found that actually some papers we have published where we have found that this role of this carbon atom is not much, it's very little. And what another thing we found that iron bond actually is mostly back donation bond, and it's 70% or like 60%, and the other one like the donation for nitrogen is very low. Okay, I'll talk to that. So these are the systems we are currently modeling, and I just take some example. So there are some system which is actually by work on the carbene compound in Induced group. That time we published a paper on iron, also Vitran group published a paper. And then their paper following work, that guy who did the work with Vitran, he moved to Professor Jonas group, and he did also nitrogen binding. So being attracted this, now we have tried to see how it binds and what are the interactions which are responsible. So these are the things that are missing in the literature. No, there's just a qualitative guess that donation, back donation, but really with pinpoint accuracy, what are the amount and which are the orbitals involved, how they're interacting, are not properly studied. I mean, not reported. So we took their system, optimized them, and what they found that at below -80 centigrade, it binds with the nitrogen. If you heat it up little to dissociate, and then electrochemically put proton, and the real what is it called? It's very milder condition. You have to take ether and like some borate proton source, and then you actually can make ammonia. Okay. So what he did actually, we took their system and optimized them and did EDUNSB analysis. And we found that the majorly it is actually EDUNSB is nothing but you take a compound and write oxygen state, you write your ground state, you optimize it, and then you actually fragment the certain bond. You want one bond or more than one bonds, and then imagine that take the fragments in the excited state, and your calculation allows you to from the complex in the ground state, and on particular bonds you can actually get which are the orbitals interacting, how much is the interaction energy, how much Pauling repulsion energy, how much electrostatic, how much dispersion energies, how much covalent energies, all you can find out. Okay, so for this calculation, these are the fragments into and the this iron center. So and then the orbitals, if you match and try to do this calculation, you find majorly this is a charge flow from these are the red to blue. So first one, suppose left side is the one where the charge is flowing from nitrogen to the metal, and the next one you give metal to the nitrogen is the back donation, and all these values are given in the bottom 61 and the 51. These are the energy stabilization because of these interactions, and we can exactly find out the orbitals which are involved in these interactions, and where we can speak fundamentally about the electrostatic interaction force, then the covalency in the character, how much is the other orbital interaction, how much electrostatic interaction, how much dispersion forces, and what will be the interaction energy overall. Okay, and then we can also find out that what is the bond energy of those. Okay, so by doing that one, we found that they have actually major 4 types of interaction, and the last one actually that is kind of charge deflection is like a kind of also covalent interaction along the bond, and all these are color coded. So red to blue actually charge migration, and by doing that we can actually find it so these are the right side, the summary. So if you take the complex with the 2 kayak with the iron with the nitrogen bonded neutral state is equal to 1, and then the anionic state, when you reduce it, you have to take 1 electron, then you have to put on the nitrogen, and then what you do, then we try to calculate, and they found that this is the anionic species has little bit less interaction energy than the neutral one. And how they get stabilized because of this electrostatic force between the anionic species and the cation like potassium and all. Okay, like here. So these are the forces, and then our we all kind of interactions we pointed out, and this is our one of the work. And then we move to another system where actually this is by Pollard. They also came up with a system where they try to make mimic system like a model system where the carbon and these iron interactions and the nitrogen bonding the role. So they then we took the system and try to say that if you try to do the reduction, and then what it does, the nitrogenase enzyme in the resting state, it has spin state equal to is equal to 3/2. It doesn't bind to the nitrogen. So you have to electrochemically it undergo reduction from the S4 Fe4 unit on the expense of what we call it ATP, a magnesium ATP energy converting to ATP, and the electron transfer happens, nitrogen got reduced, and then protonation happens. Also, there is a hydrogen formation and all of that. It's a big complicated process. So what they do, and then there is a point that the sulfur iron bond breakage or like elongation of this bond, those kind of confusions are there. So because it's in the enzyme, you can really not study much. So they make a system where is the iron is sitting on the pi cloud or the benzene and sulfur bond, and they try to show that if you do that, and then one of the sulfur bond can break in the what we have taken where it's already broken one. So by modeling on, we have found that these are actually the system where the interaction energy also like same like the previous one, and these are the deformation densities and all. Okay, so I'm not going into detail analysis. I'm just giving overview, and this is another system where one of the Indian professor from cultivation of science, they use this trinuclear nickel 2 complex, okay, and which actually electrochemically can form this what do you call it, hydrogen, not ammonia. So we also try to model it to how the binding happens and how what's the mode of the reactions, because the paper only give that there are many kinds of possibilities and they have not given any of the calculations or any idea. So what we did, we have optimized. We found that when the nitrogen goes, it gives some stability, and the cavity opens up. And then if you do the put electron electrochemically, one of the nickel center goes to nickel 1 plus from 2 plus, and then binds to the nitrogen. And then we can see that the central one can bind, or the side one can bind. And by doing our calculation, we found that these are the all calculation which proves that the interaction energies and orbitals and all. We found that that when you have it, the middle one, the central one binds, it is giving more interaction energy than the terminal one. And also we tried to by doing the protonation and all, we found that the reaction proceed like this: first encapsulate the nitrogen, and then it is actually binds to the central one, maybe the side one. But after further electron addition, it actually mostly binds to the central one. So this is the way it goes. And finally, distal or the alternative process is involved, and we have not studied that. Okay. So now next one we have gone. This is recently paper in our Journal of Computational Chemistry, which could be also cover page of the journal, and where we have studied that famous molecule, our Professor Brownsieg, who came here, gave a talk in our institute, and we have taken their borylene complex compounds, and also the compound which is actually before Brownsieg made by aminoborylene by Betrons, and then we have taken why the compound containing B-dur group by Brownsieg et al. Can bind to the nitrogen, and but not the one which is aminoborylene by the Betrons work. And then all we studied, we looked to ED study, and then found these are the system which actually metal free. So boron system, which are very exotic, and the metal free system, they can actually do nitrogen binding and can be activated by electrochemical way or like chemical way. You put electron source like potassium graphite and proton source like R4BH plus like that, and then you can actually try to protonate them in solution. Okay. So nitrogen actually, I'm not going to the basic. This is the orbital diagram and the interaction of the metal nitrogen, and also the some of the sonar, the boron metal interaction, boron nitrogen interactions. And these are the systems we all study, their chemical bonding interactions, and we found many things which are interesting, and where we have found that this is major back donation from the boron to the actually the nitrogen, which actually is important, and the sigma donation from nitrogen towards the boron is less. And also we found that people are believing that these radicals are which in this process were formed. Sometimes it is a carbon center, but we found it is actually boron center. And I'm not going to much to the detail of the study. And and when you have an amino group, it also donates the electron to the boron and doesn't like let the nitrogen to bind. We have found that this bond is stable, but energetically this species having this 1C is actually the one which doesn't which is energetically very higher energy by 15 kilocalories per mole. So the nitrogen binding is thermodynamically not favorable. Okay, so you need to have instead of a in TMS group, you need a aryl group, and there is a article by Mo et al. So where they have done blog EST calculation, where they have showed that instead of this in TMS or like a B group, you can have CF3 group, those kind of group which can enhance nitrogen binding. Okay, mostly those are theoretical studies. And also recently have shown you can have the analogous to CAG borylene. You can take like CAG silicon or CAG germanium in between. You can see whether they can bind nitrogen. And this also we have published recently. And we have shown also this kind of systems are possible. You need very bulky group around the CAG carbene or nitrogen on the side, where this should not try to dimerize the silicon or germanium. It should try to repel them more, and then nitrogen can bind. And because the interaction energy is 60% to that of the cell bind and dimerization of the silicon or germanium. Okay. So now I go to our experimental studies, where actually we have developed a catalyst, and which called nickel 4 catalyst left side. It's like heterocubane. And by mass spectrometry, you have analyzed that which are the intermediates it goes through, and all of them we have studied by mass spectrometry, and also have some of these are the one we have also isolated. Okay, and we have also seen that this nickel 4 can on a solution undergo oligomerization. So and then it undergo oligomerization means it will split into monomer, and then or the dimer and the trimer, tetramer, 2 till octamer we have seen, and they are in equilibrium. But when you try to crystallize, all you get this tetramer. Okay, maybe it has the maximum stability. So this is the structure of this complex. So what we have seen that if you try to keep in air for some days, it can bind with the nitrogen, and we have studied by mass spectrometry. It can be pentamer and tetramer. they're binding with the nitrogen. And then what we did, we tried to put electron. I did CV, where we have seen that I go back to the CV, that it can also it can actually undergo reduction. So we are thinking maybe the cluster is undergoing reduction, one of the nickel center out of 4. But later on, we found that actually for mass spectrometry, this equal be like these oligomers are no longer present. Only you have some monomers when you put electron. Okay, so this schemes, then we thought of that. Okay, you have a this tetramer in solution, solid state, it dissolved in solution. It is actually in oligomers. Then you put electron, it only goes to monomer, and in the electrochemical condition, it can bind to the nitrogen, and you can protonate them. All these species we have actually characterized by mass spectrometry. And in in parallel, it has been used by Kodanoman's group, and they have shown it has very high nitrogen to ammonia conversion, 26.5% Faraday efficiency, which is highest in the literature. Okay, so this is the way it goes: monomer, dimer, and all this. Okay, so and then this is the oligomers what we have shown and probed by mass spectrometry, and you can see it's a the tetramer you take in orange color, red color. You put potassium graphite, it goes to like dark brown color, and possibly here nitrogen binding happening, and nickel 2 plus to nickel 1 formation is happening. And we can we have characterized the nickel 1 plus by this this PTR, and these are the picture, the electron density from the Orca calculation. And by the UV visual spectroscopy, you can see somewhere around 450 it is this on reduction, the intensity of the UV visible band is going down, and around 300 nanometers is going up. And these are the species, and this is our actually observation. So we can have all species in equilibrium, put electron, it bottom down to the monomeric anionic unit, and then it can bind. So the one of the problem with the nitrogen reduction is that the nitrogen is actually in free state. It is actually very much non-polar, and we cannot add free electron and proton because its electron in affinity is negative, and it's a problem. So with the metal center moment to bind it, and it can part of this electron density and to the binding and through the buyback donation and all. So we found that when you model it and the monomer with this neutral state, it has a good binding, like around 4 kilocalorie. It can delta G 4 kilocalorie per mole. It can which is exothermic kind of, which binds, but it has this species can take electron and undergo reduction, and very electron affinity is very high. So even it can take more, and all these are for calculation. And now we are proving the fragment in solution. So monomer, dimer, and this even monomer we can actually trap with the other unit and is in this form. Okay. And then we have also proven that this tetramer and pentamer in solution also can bind with the nitrogen, and exactly it fits with the expected mass values. Okay. And also this monomer can bind with water or water acetonitrile or nitrogen. All the mass fragments actually have proven. And then electrochemical, you can protonate them. So we have done the reaction then set the glove box by electron addition, and then we took into the nitrogen line, and where we have tried to pass bubble nitrogen, and then we tried to do mass spectrometry. We have found the after the nitrogen protonation, these are the masses exactly matching. Okay, so these are the part by electrochemical studies from Professor Raman's group. So the Tamil Selvi from their lab, they studied that they proven that it can produce ammonia, and this is the right side orange picture, actually the one where they are this is the from literature till now 93.3% are nickel based material which can electrochemically do nitrogen reduction. So our one is the till highest one, it is 26.5% Faraday efficiency, and the flow rate the production rate of around 35%.
5 more minutes to go.
Yeah, so I'm going yeah, so this is the way we think it goes. Okay, and nitrogen binding electrochemical reduction, and we have done. And these are our ED calculation, where we found this type of bond, the nature of the interactions, and the all we have studied by the calculation. And these are our summary of the ED calculation: electron density from red to blue region where they're migrating, and these are the stabilization force. Okay, and this is for the anionic species with the nitrogen, and with the potentiated one also in the it was. And then we have studied the subsequent photon addition to prove also whether it is going through what we call it distal or alternative path, and we found that this steps these energetics thermodynamic energies for this reduction actually are favorable, they are negative. Okay, So in conclusion, my talk, we are just have it really studied by ED-UNICV calculation, the metal nitrogen bonds and the role of lighting events there. And also we have studied the non-metal nitrogen like boron systems, silicon, germanium. And we found that nitrogen to ammonia reduction electrochem possible. And we have developed a catalyst in collaboration with the studies from Professor Kodanaman's group. And we found the nitrogen nickel binding direction is much weaker than the iron nitrogen. And literature, you will see that many nitrogen nickel nitrogen systems under vacuum, they just lose nitrogen, but iron system, they don't do it because of this. And there are a lot of power dispersion forces are acting in the bond. Okay. So thank you for the opportunity to speak about it. And I like to thank IIT Madras for seed grant and DST and further, I'm looking for some funding too. Thank you very much.
Thank you. Very nice to see this involvement in understanding new catalysts, the process of reduction, the steps involved, etc. And this is a very important problem for humanity to address if we were to look at new catalysts and also at even at atmospheric pressures. So do you think this is really a feasibility that you can replace the the great catalyst that we have for ammonia? This one question. And what kind of new things that one can offer when it comes to, today everyone is talking about green ammonia.
Okay. Yeah, so the Haber-Bosch process is the one which is actually the process and we make tons of ammonia, and which is actually more major and ammonia products are made by actually this ribosome bacteria or azotobacteria. There are some 174 gigaton per year. Okay, but these systems are actually much weaker and they are doing catalytically and very low amount. So, but one of the things that these are cleaner processes what we are trying to develop, and these our like Haber-Bosch process they studied, and that is actually operating at high temperature, and they need a lot of energy, carbon source, and you make carbon dioxide and all. That's the reason these are actually under research. So it is, I cannot say that we have to do a lot of research. Maybe some kind of system we can find where it can do it much more efficiently, and one day it could go to the industry. So in fact, where I did my PhD, Karlsruhe, there is a pillar where actually this Haber actually developed this ammonia, and that pillar is still there in Karlsruhe University left side, and he was making initially with this osmium or ruthenium catalyst 125 ml per hour, and then within 5 years, Bosch in around the same that's a BSF, and which is actually just 50 kilometers away from the city, and they took it, and then with another guy called Mitzvah, and they developed this alpha iron 0 and coated with iron oxide.
Sure.
They did it. I mean that they developed in 5 years, and then they started producing in tons in other years, and now we are producing a lot of it. Yeah, I mean we are very far from there.
So you think in the green ammonia process, these catalysts that are being developed, molecular catalysts, will become useful?
Yes. Definitely they'll be useful, and with the initial stages, and we should find the better, which will bind more efficiently. The ligand factors are important, where it should minimize the hydrogen plus to H2 formation and should promote only the nitrogen reduction. So that is what actually these catalysts are doing in our catalysts also. We found that what potential it reduces hydrogen production and maximizes ammonia production. And then these are the initial results, but definitely there are processes like, since we are working the nanofield, there is a system where they use gold nanoparticles and they couple with the nickel nanoparticles, and they found this Faraday efficiency around 67%. It's quite a lot. So
so Sundar Gopal, let's ask his question.
So I will very quickly the same line as Pradeep was asking you. I mean, in terms of the same like nitrogen activation, I mean, in terms of stability going to the industry and all. So what do you think about it? Your comment?
Yeah, I mean that we are not there to go to the industry. No, none of the scientists. but there's a research over like last 25 years people are doing. And now there's actually now what mode is coming, like lot of metal catalysts have been.
So Karthik, now you know that what Holger Braunschweig recently did.
I'm well aware of this, and their system actually not reversible, not cyclic also, because of the covalent bond between the boron and the nitrogen. Okay, so that is not cyclic. It is only that it is irreversible and cyclic once. Most of the step, but one step not cyclic. So it also has problem. They need to develop new catalysts where they can do it. And boron system will be good because I have also seen a lot of nickel boron or like iron boron systems. They're polymeric and they are electrochemically can do nitrogen reduction. Those papers are in the physical chemistry journal.
Thank you. Redmi, I don't know who is this, but you have a question. Karthik, you can see that on the chat box. Who is Redmi?
Okay, 1 minute, please.
Okay. You can't hear that person. Well, Karthik, you please look at that. Bodharaju, yeah, Bodharaju, you have a question. He's calling, asking this question from Korea, it appears like.
I'm wondering if you have used nickel monomer directly to see nickel. Okay, actually, we cannot isolate the nickel monomer. We can isolate the nickel monomer with phosphine ligand. If you allow phosphine in it, like diphenyl phosphine, we can get monomer. But problem happens when we try to do the same catalytic study. This phosphine blocks the nitrogen side because it is very good donor, much better donor than the nitrogen gas itself. So that's the reason.
Thank you, Karthik. So that Bodharaju, you have roughly got the answer.
Yeah.
Thank you, Karthik, for this nice presentation. Great potential, lots of possibilities, and hopefully this will one day go to industry. Thank you. All the very best to you. The last talk this evening is Raghavendra Sai's talk. So please go ahead and make your presentation. I'm not going to introduce you as I have not introduced anyone, and this is really not necessary, and you have been here for some time. Yeah, thank you very much. 20 minutes. And then I'll give you, a warning. Sure. 5 more minutes to go. Yeah, thank you.
Thank you for the opportunity to discuss our work with all of you here. We work on fiber optic sensors for clinical diagnostics and mostly environmental and monitoring and food safety monitoring. And we see that this can be applied for biomolecular interactions as well. So I work in biomedical engineering group in the Department of Applied Mechanics. I have joined here in 2011. Before that, I was 2 years postdoc. I did in University of Idaho, very little known one. And then before that at IIT Bombay, PhD. So this slide is not for us. Okay, so the research objectives have been basically over the last 10 years. We are focusing on whether we can develop certain technologies as simple as glucometers or pregnancy test kits. As you know that you typically have to go to laboratory or a sample collection center, give the sample, and you typically wait for blood sample or urine sample. You wait for the results till the evening or next day many times, right? So if we imagine most of our population, these tests are not really available to them as quickly as we do have. So our idea is to see if we can bring some of these technologies, make them available for most of our citizens in India. So with that, let me go on. And of late, our research focus has been mainly on automolar analyte sensing technologies. So there is recently a review paper published by our group in collaboration with Dr. Urban Marcosi. Our guys have put 95% or more efforts on this. So I thank them very much. So coming to this lateral flow assay, everyone is aware of. This is a pregnancy test kit is one good example that you see in the market. So it's a very simple technology. Of course, a lot of research has gone in. It originated in Finland, in fact, and then over the last 20 years, this has revolutionized clinical diagnostics. But however, it does have some limitations, mainly with respect to sensitivity and dynamic range and quantification. Of course, it's a good naked eye system, but unfortunately, if you want to quantify, you need readers or mobile phone like that, but still there are issues. So our focus is basically to develop some sensors for various applications, including clinical diagnostics, water, food safety, and probably these technologies can be applied to pharma as well as agri industries. So what we make use of is fiber optics and noble metal nanoparticles, which exhibit phenomena such as low plasmonic resonance. So just to give a brief introduction about why this fiber optics, if you can imagine something with light, you probably you recall the double beam UV visible spectrometer, which used to be a big 2 feet by 3 feet laboratory equipment, and now it has gone down to hardly half 1 square foot or less. So absorbance measurements are really important. We have been using them, and mostly they give you typically the instrumentation becomes quite simple, so that you will be able to you can imagine how you will be able to devise a handheld device. So this events and wave absorbance, if we particularly talk about, it's very interesting phenomena when light gets reflected, at the interface, air-water interface of any refractive index contrast. Basically, typically you see that there is evanescent field at the point of reflection. So why is it so important? In fact, if you can actually place a fluorophore or a chromophore at that interface, just on the outside. So what happens is this fluorophore can actually get excited by the light passing through the fiber or a waveguide, and then you can actually see fluorescence, right? So that's a very interesting phenomenon, and this is a near field phenomenon. It's hardly 1/10 of the wavelength of light. So for example, if you take green wavelength, the depth of penetration is hardly 50 nanometers. So you don't need washing steps or something like that. So why we are using optical fiber? When we use optical fiber, here also you have this evanescent wave. What happens is the fiber has got a core and cladding, and you need to remove the cladding so that you can access the core of the fiber where the light path propagates. Most of the times in a simple straight fiber, I'm talking about multimode fibers, not communication fibers. In a simple optical fiber, the evanescent field strength is less. That may actually give you some result, but if you want to increase it, you somehow need to modify the geometry. So this is one example where you see that we took 200 micron fiber, the core. So what you see is 200 micron, and we have bent it into a U shape. Why we do it is, when we do it, you'll see that the light matter interaction improves. And the best thing is, if you can actually functionalize this optical fiber, maybe silica fiber, or even PMMA plastic optical fiber as well, if you can functionalize and have some amine functional groups, and you dip it in gold nanoparticle solution, as more and more nanoparticles adsorb to the surface, you actually see more and more absorbance through the fiber. All right. So you can actually have time scales even in few minutes also. You can in fact see that an order of 4 orders of light can get absorbed. So so these fibers, these U-bend probes, give rise to such high sensitivity, which is mainly because of evanescent waves, and we call this as evanescent wave absorbance sensitivity. So, and the beauty of this is, in fact, maybe a few tens of nanoparticles may be detected if we have very good instrumentation. So what really happens? This is a simulation that really captures about the fate of the light passing through the fiber. especially in the U-bent or U-shaped U-shaped region. So about 40% of light gets escaped and the remaining 60% propagates. And you see that most of the light is available at the outer curvature, and mostly these nanoparticles, when they come and bind, these light passing through this within the fiber can get absorbed by these gold nanoparticles. So this is the original, this is how the probe looks like, and the scale is 1 centimeter here. So as far as absorbance is concerned, you can actually get even 4 to 5 orders of light. That means if you launch about 100 milliwatt of power, on the other end, you get only 15, 20 microwatt. So whatever happens in lateral flow assay, if we try to do the same thing here, what we do is we just take a sample and then add gold nanoparticle reagent that is coated with some antibodies, and then leave it for 5-10 minutes and dip the fiber probe coated with antibodies. What you see is a sandwich immunoassay you will be able to realize on the fiber surface. And the instrumentation that you can use is a very simple one. What you see is the instrumentation. There is nothing in the behind any big box or any black box. What you have is a light source with a constant current supply, and it's a photodetector with a console and the computer. So with that, what you see is very remarkable response. We were able to observe that these fibers, these probes, can actually detect human IgG as an analyte. If you take, they'll be able to detect. They were able to detect concentrations down to 1 femtogram per ml. So what does it mean is basically that correspond to about 151 zeptomole or about 10 to 15 attomolar concentrations. So this is, and one more important thing is there is no washing step involved. It's real-time binding response you will be able to observe, and in 20 minutes this is the response. So just to confirm whether this is something that is really happening because of specific detection or some non-specific binding, we just did a silver enhancement, or you can say silver reduction on this gold nanoparticles, and you see that there is a 25% enhancement, 25 times enhancement in the sensitivity, and you indeed see distinguishable response from each concentration. And whereas the control is below this 1 femtogram per ml. And the volumes that you take are quite small. The sample volume is 25 microliters, and then the conjugates 25 microliters at a OD of this much. So another beauty of this system is that you will be able to fine tune the dynamic range, which is very important for clinical diagnostics. If you want higher dynamic range, that means you can actually use gold nanoparticles that are small in size, because the extinction coefficient of these gold nanoparticles, when you go down, it's smaller, and when you go up 40, it is higher. So almost 10 times improvement in extinction coefficient when you go from 13 to 40 nanometers. So we try to compare what we have seen with these probes with what is kind of the first report on attomolar analyte detection by Chad Merkin and co-workers way back in 2003. It involves, it's a very nice technique. It's known as Biobarcode Assay. It involves magnetic nanoparticle sandwich assay, and then extraction of these labels, again perform a sandwich, nucleic acid assay, and then amplification steps, about 4 to 5 steps. All that you can actually see that this is reduced to 2 steps with the use of efficient transducer and a very efficient label, which is gold nanoparticle here. So further to confirm whether what we are getting is real or not, we have used similar volumes to see whether Biocore SPR system is able to detect these concentrations? Yes, it does, because it's very highly sensitive system. And what you see is we have just used only the constant volumes that we typically have used for the assay. So that means we have only a very short window of binding reactions observed. But however, we did see some response. So that means we have co-validated this technique, that what the results that we are getting is really indeed right. Because there was a comment when we submitted this to ACS sensors way back in 2016, they have asked us to check our calculations. So, probably nothing can be more insulting than that. We have to bear with that. So, the instrumentation is good, no washing steps. So this actually qualifies closer to, there is something called as assured criteria given for point of care diagnostic devices. It stands for affordable, sensitive, specific, user-friendly, rapid, equipment-free, and delivered. However, it does have some limitations. So far the results are only within buffer, but not in serum. Serum, we have to definitely dilute it 100 times so that the diffusion limitations can be overcome. And the manufacturing, we are slowly inching towards the technology development will show. We have just done an actual analyte detection, of course, in laboratory settings. The analyte called as mannose lipoalbinomannan, which is a TB marker in urine. TB is a very critical disease, infectious disease in India. 25% of world's load, disease load in India, about 25 lakh cases annually. The government is very keen on controlling TB, but diagnostics is an issue. So we have come up with this, and we did see that this assay work for this TB lamp down to sub-femtomolar concentrations. So we are also looking for alternate techniques like polymeric optical fiber, which are very cheap and very easy to fabricate, but however, very difficult to functionalize them, and that's how their use is quite limited. So we did also develop some label-free plasmonic sensors that work. We are yet to pursue it further, mainly because the facilities that we had earlier were not existing anymore, like sputtering unit. So we have worked on seed-mediated growth of plasmonic. We want to generate plasmonic sensors by simple chemistry, seed-mediated growth. These are some of the nanostructures that we have developed on an optical fiber. So quite interesting. So one interesting part is this is unpublished data where we just took seeds and then immobilized them on the U-bend optical fiber. We grew silver on it, and we see that different shapes have been formed. And then the moment we dip it in gold solution, growth solution, the truncation has happened, and then subsequently growth took place. So we were able to observe this everything in real time. This is one of the kind of first observations thanks to this U-bend probes. But we were not able to complete these studies as yet. So the truncated ones, so seeds, if you have silver seeds, and then basically silver core gets formed, it gets truncated when we dip in gold solution, and then growth starts. Very nice phenomenon. So about technology development, here the key technique is the key technology is the U-bend probe. Earlier, we used to manually make these probes using a candle flame or butane flame. Now we have, and then we started working on developing technology for this. We started with the butane flames, but the flame was quite difficult to control, quite dangerous. So we then came up with this laser bending machine developed in the lab, where we used CO2 laser and optics mirrors basically to focus this laser onto the U-bend probe, and this has a robotic articulating mechanism where the fiber is held and then bent automatically. So, and this is the device that is under development. You see that this is the first version where we actually used a simple Arduino microcontroller, and we have made a custom optical coupling unit where we simply use this U-bend probe, put in a paper cartridge in a simple spring-loaded system. So this is under evaluation. We see that the sensitivity needs to be improved. We are working on that. And then subsequently, we also, you see that in this slide, you see this is a single test use, but in many cases, you actually need multiplexing. So where you in fact need about, let us say, 8 probes at a time. Why we chose 8 probes is basically the well plates that typically the biologists or pathologists use is having 8 wells in a row. So we have developed a 8-channel fiber optic absorbance biosensor. We call it as RFAB. So this is, we are actually, we have an Indo-German science and technology project, a phase 2 extension of our project, mainly to develop this technology, demonstrate it. So what you can do with this is basically, one can actually talk about doing label-free sensing, labeled plasmonic sensing, as well as event wave absorbance sensing, where you can actually detect biomolecules or bacteria that have absorption, for example, at 280 nanometers. So, okay. So what we want to do, currently we are focusing on TB. We are in discussion with some private labs as well as NIRT to test the real samples, and subsequently we are also, we just have got a kind of approval for the project for ovarian cancer diagnosis, where we'll be using this RFAB. We would like to deploy these devices in primary healthcare centers and see whether they are going to meet the unmet needs. So with that, I thank you very much. This is the team. This is an old photo, but however, most important people who have contributed to this lab are all here, and acknowledgements to the lab members as well as collaborators, former colleagues, and funding agencies. Thank you very much.
Well, very nice. Great presentation, great technology, a lot of promise in point of care diagnosis. So obviously, 2 things as a chemist would ask. One is kinetics of any given process. You touched upon that when you started probing the plasmonic particles evolution, although it is not complete. So kinetics is something that one can look at. What are those kinetic events which are monitorable in a seconds or minutes kind of time scale? Polymerization, one such important thing. Biochemical evolution is another important thing. At a single cell level, if these things are monitored, or organism level, or a muscle, or some kind of a tissue level, these are all great. I'm sure that you are exploring or looking at that possibility. Kinetics in general. Huh?
Right. So this RFAB that you see, this is when I say biomolecular interactions, we are actually looking at binding kinetics. So one way is basically we can actually make use of simple events and wave absorbance. We don't need to go for SPR or anything like that. These probes actually have this absorbance sensitivity. So one can actually monitor binding of biomolecules, or if the pathogens or bacteria or the cells, if there is any colorimetric change that is happening, that we can have, that can be detected using these probes without use of SPR or interference phenomena.
So the second thing is, as far as people are concerned at the primary health center level, they want to mark, let us say, 3 or 4 parameters in one go, super fast. Now that can be use and throw kind of sensors and things. Now, what stage are we with regard to such a deployment of, let us say, multi-parameter sensor devices?
Right. So as of now, there is no technology, but however, there are a lot of startups in this area over the last 5 years, and any technology can hit market anytime. So that's how the thing is, and definitely one of the major problems is in this diagnostics field is not really the technologies, but it is the biomolecules that cause a big problem to us. So all technologies do work, but the moment we actually handle the real samples, the issues crop up, and many times all these technologies end up not, overcoming these challenges. So for that, we in fact are collaborating with the clinicians, not really clinicians, but clinical diagnostics people mainly, to see, understand these challenges first.
The specificity is the key thing, and that is where biomolecules are required, and that is where challenges are. How do you see DNA nanotechnology getting in there? Because after all, you can design something and get something, and then somebody will ship it to you.
Right. So you mean DNA diagnostic technologies?
Specific DNA devices that you can make, by DNA nanotech, by specifically targeting. And if that is in a position, everyone is moving towards molecular medicine.
Right, right. So yeah, these platforms can be used for nucleic acid diagnostics as well. So those studies they are in the process. We in fact try to go into nucleic acid detection, but we still have some way to go before we can publish something.
Sure.
But this technology can be used there as well.
Absolutely. Are there other questions, colleagues? Well, then I don't see questions and other than this. So thank you very much, Sai, for that wonderful talk and the great promise that your technologies. And I know that you need greater support and students, and now the labs are all open, and all of these is very much needed. I see that the diverse anisotropic nanostructures is a great possibility for coupling that with Raman and several others as well. In fact, we are in the laboratory. Anantu is here it was there. Yeah, he is here. He is making nano clusters and crystals of that on tiny tips, and similar kind of growth may be possible on your devices as well for better detection. So all that is great, and thank you very much. So today we had 4 talks, fantastic talks, and lots of possibilities. So we'll see, we'll meet each other next month. In case you people have ideas about giving a presentation, and in case you wish to suggest somebody, please do get in touch with us. Thank you very much. Good night.
Good night, Pradeep.
Good night. Good night, Sundar. Good night.